Hello, welcome you all to this on-demand live session. We will be mainly focusing on linear algebra and especially week 5. I saw the questions that have been posted through this spreadsheet, and it literally covers every topic from week 3 to week 6. So we decided to divide sessions into more than one live session. So most probably there will be another live session in which week 6 will be prime focus. Today we will be focusing mostly on week 5. And again for week 5 also I have seen questions are from almost all topics. Am I audible? Anyone can confirm?
Yes, are you audible?
Okay. And okay, I'm seeing only very few participants. I think most of you have asked questions, right?
So today, it will be like a general revision, or like will it be like a specific question answer session?
Yeah, so it will go both ways because when I saw the questions, it was like there was doubt in almost every topic. So I prepared a presentation so that I can touch upon each of the topic, and I'll try to make it simplistic, and then I'll take your doubts also. Both things will be done today.
Okay, sir. Okay.
If that suffices, we'll be having one more session where we will be covering rest of the topics because the topics in themselves are very, very large.
Yes, sir. Yes.
Yeah. Okay. So can I move to the presentation that I have made?
Yes, sir. Yes.
Okay. So is it visible or do I need to zoom in?
It is okay, sir.
It's visible, sir.
Okay. So basically our prime focus is week 5. Anyone having any doubt from week 3 and week 4 may please ask now. So if the doubts are small, I'll clarify it right now. I saw very few questions from week 3 and week 4. So there was a question on fundamental subspaces. So I think I have covered that in Solve with Us session of week 3. Okay, so then we will proceed. Achha. The first topic which is covered in week 5 is complex matrices. So the name itself suggests if the entries or some of the entries in a matrix are complex, then we call it a complex matrix. Okay, so it looks something like this: a equal to 8 plus I 0. So there is a term having I, right, or iota. So so there was a doubt from last term, which I want to tell you. Someone asked me why we write numbers like this, complex representation. So I think people here are clear with that, right?
Yes, sir. Yes.
No doubt in representation at least.
The I is basically because we don't have a fixed number for the square root of -1, right? Like that's the only reason, right?
Yeah, so that is a theoretical aspect of this complex number, that we do not have root of -1, so we write it as I. But see, there are situations where actually there are terms, but we use I with it. For instance, suppose I have a vehicle which is moving in northeast direction at 45 km/h. Okay. Now suppose I want to write it into its north and east component. Are you getting me what I am saying?
Yes.
Yeah. So how will I write it? I'll write it 45 sine 45, that will be in north direction, and 45 cos 45, which will be in east direction, right?
Yes, yes.
Yeah. So while writing such numbers, what we do? We do 45 cos 45 plus j or I 45 sin 45. So whenever we
Yes.
have two components which are perpendicular to each other, there also we use this I and j. So it need not be imaginary always. It may be two components which are in different directions. And we want to show that this particular thing is actually split into two parts. There also
Okay.
we go with I and j representation. Okay. So
Yes,
that is
yes.
again a physical part of it. So if any of one of you is from electronics or electrical background, so they may relate to the current. There are two kinds of current. One is reactive and one is active. So that is at 90-degree. Again, the phase shift is represented by J, which is a 90-degree phase shift. So in such cases also we use I and J representation. Okay. So that was the first part. So if we have such quantities which have components in different directions, we are going to have this I or J representation. And when these entries are entered into matrices, we call it a complex matrix. Nothing more than that. Okay. Now what is the next part? Next part is Hermitian matrix. So whenever there is a complex matrix whose conjugate transpose is same to it, I mean it is equal to its conjugate transpose, then we call such a matrix as
Hermitian.
ith row and jth column. Prash, I am not able to understand. Can you unmute yourself?
Sir, I am talking about I, where we use I.
No, so that meaning was different. That is just a canonical representation. That has nothing to do with I and J, which I was talking about. Okay.
Okay, sir.
Yeah. So Hermitian matrix is something when we take conjugate transpose and the result is same as the original matrix, we call it as a Hermitian matrix. Okay. So it is similar to symmetric matrix in real case. So just remember these things. I mean, there can be a similarity that you can drive out, or you can take it as a conclusion that when we are talking about real symmetric matrix in real space, it is similar to Hermitian matrix in complex space. Okay. So there will be an orthogonal matrix in real space, which will be similar to unitary matrix in complex space. So and so. There will be so many things which will be similar. So there will be an eigenvalue decomposition in real space. Similar to that, there will be a singular value decomposition in complex space. Okay. So let's move ahead. Next thing, very few properties of Hermitian matrix which are relevant to this course and machine learning. First thing, all eigenvalues of a Hermitian matrix are real. And I think Prashant sir has given a very good proof of it in his video lectures. So you can go through it and you will understand why and how all eigenvalues of a Hermitian matrix are real. Okay. Next property is eigenvectors corresponding to different eigenvalues of a Hermitian matrix are orthogonal. Okay, so this is again proved by Prashant, and these two proofs are very easy. So I did not touch upon it because that were self-intuitive. So if you have any doubt in these proofs, you may ask me.
Yes, there was a question I saw this morning
Okay.
regarding the proof in the discourse forum.
Okay.
So it was regarding the lambda of Hermitian being real, right?
Yeah.
So in that, the LHS side, like it is x star. It comes down to x star times lambda star times x equals lambda times x star times x, something like that, right?
Okay.
So, but if we go back upwards, like we will be able to, like we have shifted that x star from the left side to the right side of lambda
Okay.
star.
Yeah, I got you. I got your point. So the thing is, see, first point, when you see the properties of Hermitian matrix, what we are saying, eigenvalues are real, okay?
Yeah.
When we are saying that, it means lambda is a scalar. Real value means it's a scalar, right?
Yeah.
So if you move it, I mean, if you pre-multiply or post-multiply, will it make any difference?
Yeah, but no, sir, no.
See, when we are multiplying A, B, so if A and B are matrices, order matters.
Yeah.
AB is not equal to BA in general. But when we are multiplying AB, which are real or which are scalars, AB equal to BA.
Yes.
So in that
But-
way, order doesn't matter.
But actually, this is the proof that lambda is real, right?
Yeah. So what sir is, I'll explain you every step. Okay. What sir has said. So first thing, it starts with eigen equation AX equal to lambda X. Okay.
Yes.
Then sir has taken this Hermitian on both sides.
Yeah.
When you are taking Hermitian on both sides, you are so it's just like taking transpose of AB. So AB transpose equal to B transpose A transpose. Similar to that, AX Hermitian will be equal to X star A star.
Yes.
Correct?
Yes. Yes.
Now he is post multiplying both sides by X.
Yes.
Okay. Now here there can be a confusion. What is lambda star? So see, lambda is real. So lambda is not real. I mean, we have not proved it. Okay. So let it be lambda. Okay. So lambda is number. Don't call it real. It's a number. Okay. It can be real or complex.
Okay.
Okay. Now, what is a Hermitian of a number? Real or complex? So for a real number, it will be same. So if there is 3, its Hermitian will be 3. If there is 3 plus I, its Hermitian will be 3 minus I.
Yes. Yes.
Correct? It means it's conjugate.
Yes. Yes. Because we don't have a trans. It will be a one time. Right?
Yeah, correct. It's a one-dimensional thing.
Yeah.
So for one-dimensional thing, there will be no conjugate. So lambda star is equal to lambda bar.
Yeah.
Next, what sir has done? Sir has post multiplied both sides by x. Correct?
Yes.
Now,
Yes.
x star x is nothing but I.
Yeah.
Correct? So
Yes. Yes.
that we can use. Otherwise, what sir has done? See, what we are saying A is Hermitian. So A star will be equal to A.
Yes.
So now AX, we already know AX equal to lambda X. So we can replace AX by lambda X. So our statement becomes X star lambda X equal to lambda conjugate X star X.
Yes. Yes.
Now we can move lambda to left side. That is because lambda is a scalar. So if you pre-multiply, post-multiply, it has similar effect. No change in effect.
Okay. This. Okay. This is because. Okay, I got it. So it is because we are taking. Okay, we are taking for each lambda, right?
Yeah, correct.
Okay.
Yeah.
Yeah. Look, I thought like we because the confusion was if it is a whole diagonal matrix of lambda, then
No, lambda is a eigenvalue, right? Which can be real or complex, but we are proving that since lambda equal to lambda bar, which is conjugate is equal to its real form, it means there is no imaginary part. There is only real part.
yeah.
Okay. So I think that that proof is also clear. Okay. So there was another proof for the second part. Eigenvectors corresponding to different eigenvalues of a Hermitian matrix are orthogonal. So any doubt in this?
Yes. No.
Okay. So out of these properties which sir has taken in, I think lecture 1, the lecture 1 or lecture 2, whatever. So the most important part is written here. Orthogonality implies linear independence, but the vice versa is not true. So if there are two vectors which are orthogonal, then it is guaranteed that they will be linearly independent. But if there are two vectors which have angle other than 90 degree, you cannot say that they will be dependent always. They can be linearly independent. Okay. So this part you have to keep in mind. Okay. So let's move forward and move to the next topic. Unitary matrices. Next topic covered is unitary matrices. So if there is a square matrix having orthonormal columns. So can anyone tell me what is orthonormal?
And norm is 1.
Norm is 1.
Yeah.
And okay. So norm is 1. Are you sure? I mean, what is a unit vector?
Unit vectors, it means the norm is 1 as well, right? That's what
And
unit vector.
Yeah, so for unit vector, the norm is 1 or the length is 1. So what are orthonormal vectors? So it cannot be 1. These are more than one vectors which have some relationship. When you multiply or take a product of both, you
Sir,
get,
they are perpendicular to each other.
yeah, and having a dot product 1.
One.
That is a orthonormal thing. Okay. So since the columns are orthonormal, so u star u and u star will give me I. So that is the definition of unitary matrix. Okay. Now let's. So any doubt in this definition?
No, sir.
Okay. So let's move to the property. So see, if there are there is a vector x and we multiply it with u and find the length, then what will happen? The length of ux will be equal to the length of x. Now it is intuitive. Why? Because length of ux will be nothing but length of u into length of x, and but the length of u is equal to 1. So therefore, length of x only remains. So that is an intuitive property. Next, length of eigenvalues of unitary matrix is always 1. So if you take the square root of real part and imaginary part of eigenvalues of a unitary matrix, they will always give 1. Okay. Next property is again same as Hermitian matrix. So eigenvectors corresponding to different eigenvalues of a unitary matrix are orthogonal. Okay. Any doubt in this? Any doubt in unitary matrix or the previous topic that we covered that has come up?
One doubt.
Yeah.
Actually, find a unitary matrix. Suppose if we are given 3 into 3 matrix, and if they're asking us to find it is a unitary matrix, we have to take each vectors and we have to check those are orthonormals, or we have a different methods.
See, this u star u equal to u star equal to I is the most standard method. Otherwise, what you can do, you take any two vectors. I mean, the matrix is given to you, right? Let me call its column are A, B, C. Now you find A dot B.
Okay.
Then find A dot C, then find B dot C. If all three are 0, then there is a bright chance that it is a unitary matrix.
We cannot. I mean, if it is, if all three are 0, we cannot say it is a unitary 100%.
No, we cannot say because we want A dot A equal to 1, 1, 0, 0. That is also a
okay. We need to confirm A dot A equal to 0 and A dot B equal to 1, A dot C equal to 1. Similarly, we have to go for B and C, correct?
Yeah, so best thing is go for u star u equal to u star equal to I, because the number of calculation will be exactly same.
Okay. Just
You are not saving on time when you are doing something else.
Okay. This is the simplest method. U star U is the simplest method.
Yeah, this is the simplest and most authentic. That's the thing. Even if you are taking 1-2 minutes more, at least you are reaching at the right conclusion. Okay. So
one query.
Yeah.
So when we're saying length of eigenvalue of unitary matrix is always 1, does it mean it will always be complex?
Not necessarily. Not necessarily.
But what does then, if it's a real, what does that mean? Or length of
Its value will be 1. Its value will be 1 or minus 1.
But then eigenvalue, then it's a scalar, right? I mean, it's length. I mean, how does length make sense for that?
It makes sense since if you have studied mathematics, real numbers are subpart of complex numbers. So every real number is actually a complex number with imaginary part 0.
Okay.
Okay. So any further doubt in this?
And you mentioned unitary, I mean, first property, unitary into X is equals to X, I mean, the norm of it.
Length, yeah.
And whereas unitary is a matrix, right? It's a matrix.
Yeah.
So what do you mean by length of a matrix?
Length of a matrix. So, okay. This is a tricky one. Okay, length of a matrix means so see, actually physically there is no meaning to length of a matrix. It can, columns of a matrix can have length, rows of a matrix can have length, but not the matrix itself. So there I was wrong.
Okay.
When I said that. Okay. Okay, so can we proceed?
Yes, sir.
Yeah, okay. Okay, next part is Schur's theorem. So it says for every matrix A, there exists a unitary matrix U and an upper triangular matrix T such that A equal to U T U star. Okay. Now this is true for every matrix A. Okay. So basically what it says, so if there is a matrix A, we can have a matrix, unitary matrix U and an upper triangular matrix such that this equation given in the slide is true. Okay, then in proof, again, in proof, there may be doubt because I think that was not that clear in the lecture. So I have divided that proof into 3 simple steps. Okay, first is find an eigenvalue. So when you are getting A, find its eigenvalue and corresponding eigenvector. Okay. Second step is extend that to form an orthonormal basis. So I think this step 2 you people have studied in maths too, right? Or not?
Yes.
Gram-Schmidt process is clear with everyone. What we exactly do there?
Yes.
So basically, we take another matrix or EI, a vector EI and project and find the error, right?
Okay, so what we are doing in every subsequent step in Gram-Schmidt process?
We project.
We are actually taking out those parts from the vector which can, which are not perpendicular. We are taking the parallel components out. That basically we do in Gram-Schmidt process. So that will be step 2. And step 3 is find the triangular matrix. So since A equal to UT U star, so what we can do, we can pre-multiply A with U star. So here it will be U star U on the right side. So U star U will be nothing but I. So U star A equal to ITU and multiply with U, IT U star U. So again, U star U will be I. So T equal to U star AU. From this, you can find the upper triangular matrix T. So these 3 steps, sir has explained in the proof. So I think proof is not going to be asked in any of the exam, but it is important for conceptual understanding. Any doubt in this?
No, sir.
No, right? Okay, we have to quickly move to SVD part, which is the most important. So I am just, okay. Next thing is spectral theorem. So spectral theorem, again, it says that any Hermitian matrix is unitarily diagonalizable, but the vice versa is not true. Okay, so any similar property that you have seen in the real space?
Orthogonally, like symmetric matrices, we can do orthogonally.
Yeah, correct. That is the thing. So spectral theorem is similar to that particular property, that every real symmetric matrix can be orthogonally diagonalizable. Okay, so the steps remain same again in spectral theorem, which we were doing for real symmetric case, but the only difference is here we are dealing with complex matrix. Okay. Now let's move to the most important part of week 5, singular value decomposition. So we will try to understand it very slowly and very thoroughly every step. Okay, so first thing, let's start with the definition itself. So if there is a matrix A, any matrix, it can be real, complex, it can be rectangular or square. We can write it as A equal to U sigma V transpose. Okay, where U and V are unitary matrices. So unitary matrices in case of complex and orthogonal matrix in case of real. And sigma is a diagonal matrix. So this is the basic definition of singular value decomposition. First 3 lines. Okay. Now, suppose the matrix that I am considering is a rectangular matrix and is not a square matrix. So I can say it can have m rows and n columns, where m not equal to n. Then I can write the same this equation as m cross n equal to u m cross m, sigma m cross n, and v transpose n cross n. Okay. So any doubt in this definition? I think this is a, yeah, any doubt? So this is a representation. So I think there will be no doubt. Next is, see, we are saying U and V are unitary, or we are saying U and V are orthogonal. So always keep in mind what matrix actually does. What is the physical significance of a matrix? So a matrix actually, if there is a matrix and you multiply a vector with it, so whatever that matrix is doing to that vector is the physical significance of that particular matrix, or the transformation that matrix is bringing. So for an orthogonal matrix, if you multiply it with any vector, there is always rotation. So that is the physical significance of an orthogonal matrix, that it gives rotation to a given vector, whatever you multiply with it. Okay, so U and V here in this equation are doing what? They are doing rotation, or their physical significance is to give rotation. And sigma is nothing but a diagonal matrix. So again, for a diagonal matrix, what happens? Since it has only elements in its principal diagonal and all other elements are 0, so whenever you multiply a vector with it, it can stretch or compress it. It means it scales it. It does nothing more or nothing less. So the basis direction of that particular vector never changes if you multiply it with a diagonal matrix. So here sigma is nothing but a diagonal matrix. So its work is only to stretch or compress. Okay, any doubt in this? These particular two things.
Excuse me, sir. Can I ask? You said about rotation. Like, what did you actually mean by that?
Rotation means suppose there is a vector. Let me call 0, 1. Okay. If there is a vector 0, 1, and now you multiply it with a 2 cross 2 orthogonal matrix.
Okay.
So what will happen? The resultant. So let me call that orthogonal matrix as A. Okay. And this particular vector as V. So when you multiply AV, you will get some Y.
Yes.
Now that Y will be rotated by some angle.
Okay.
So that is what we do. So from original position, it has got rotated.
Okay. Yes.
So that is the meaning of rotation.
Okay, sir.
Okay. Any further doubt in this? Anyone, these points are important. So if you are having any doubt, even the smallest of doubt, it is welcomed.
Why are we going for singular value decomposition, or what is the purpose of?
Yeah, we will come to it. Once the process is over, I have made a slide for that also. So this is the, this was the most asked question in the spreadsheet. Why we are doing this? So why we are doing this is there. Let's first understand the mathematical part of it. Then we will go to that.
Yeah.
And sir, hello.
Yeah.
Sir, like how we can obtain, if a matrix A is given, then how we can obtain U and V?
Yeah, that is also there in next subsequent slides.
Okay, fine.
Fine. So no doubt in this introduction part at least, right?
No.
No,
Okay.
sir.
No, that,
Okay, fine. Then I'll.
hello.
Yeah.
That when we are talking about like MLF, then that V transpose, when we are talking about V transpose, what does it exactly mean by multiplied by V transpose?
Multiplying. V transpose is not multiplying. So
No, U M by M cross sigma M by N cross V transpose is, no?
yeah.
So when we are crossing by V transpose means what exactly it means, the outcome.
Okay. I'll tell you that also. These things are coming up.
Okay.
Yeah. So let's move to the next slide. Okay. Next, someone asked how to find this U and V. Okay.
Yes.
So that part is getting solved here. So now we have matrix A, which was equal to what? U sigma V transpose. That we have assumed. So what we have assumed, if there is a matrix A, its singular value decomposition always exists. And its value is nothing but U sigma V transpose. So now suppose we consider A transpose. Okay. Why we are taking A transpose? We are just trying to make that rectangular matrix square, because we know there are so many beautiful properties related with square matrices, and we have dealt with it more frequently, and we know different properties also. And there is one more thing, when we are taking A transpose, it will be real symmetric as well. So for real symmetric matrices also, we have some properties that we want to use. Therefore, instead of taking A, we are taking A transpose. So the logic behind A transpose is clear, right? Why we are taking it?
Yes, sir.
Yes.
Now, when we take A transpose, what is happening? I am just taking A, then I am taking the transpose of A and multiplying it. So U sigma V transpose V sigma U transpose. Okay. Now, since we are saying V is what? Or unitary. So what we know, V transpose is nothing but V star. Correct?
Yes.
So V star V will be nothing but I. So what I am getting, U sigma I sigma U transpose, which is nothing but U sigma square U transpose. Correct? Now,
Yes.
if you see this particular thing on right hand side, the right hand most right side, U sigma U transpose, isn't it equivalent to something that we have already studied? When we have studied this real symmetric matrices diagonalization, orthogonal diagonalization, what it was? A equal to
P D
U transpose.
P inverse. Is that similar
Yeah.
matrix?
P inverse lambda P. Yeah, correct?
Yes.
Yeah. So this is similar to that, right? Since we are saying U is U is unitary or orthogonal, we can say U star equal to I, or we can say U inverse equal to U star, or U inverse equal to U transpose. Correct? So it is similar to that particular equation, P inverse AP.
Yes.
Right? So
Yes.
what we have seen basically, when we are considering A transpose, we are basically getting a eigenvalue decomposition. Correct? Eigenvalue decomposition of A transpose. So eigenvalues of A transpose, whatever we are getting, suppose it is lambda. So it will be similar to sigma square of A. Actually not similar, equal to. I should write equal to singular values of A. So singular values are not eigenvalues, first thing that you should keep in mind. We can find eigenvalues only if and only if there is a square matrix. For rectangular matrices, we cannot find eigenvalues. Therefore, we are doing all this stuff. We are making this A, which was rectangular, to a square matrix, A transpose, and we know many things about square matrices. So what we have done next, we have just written that equation and we have found out that A transpose is similar to finding the eigen decomposition. And since there is eigen decomposition, there will be eigenvalue. So can you tell me, out of these three matrices, U, sigma square and U transpose, where you can find the eigenvalues of A transpose?
In sigma square.
In sigma square. And since it's a squared value, therefore we take a square root while finding the singular values of A. Got the reason behind taking the square root?
Yes.
Correct? So,
Yes, sir.
now see, to find U, we use A transpose. This much is clear? Any doubt in this?
No, sir.
Yeah, the person who was having doubt in finding U, are you clear?
Yes, sir.
Okay. So now let's move to how to find V. Again, now the
Same.
process remains same. Every explanation that I give remains same. Only difference is instead of A transpose, what you are doing, you are taking A transpose A. Okay. So what is happening? U is getting replaced by V everywhere. So A transpose A equal to V sigma square V transpose. Again, we can see this equation is similar to eigen decomposition of A transpose A. And again, eigenvalues of A transpose A are equal to singular values of A. So from A transpose A, we are finding V. Okay.
So one question.
Yeah.
What does it mean? Eigenvalue is similar to singular value of A. What does that statement
No,
mean?
it's not similar, it's equal. I mean, singular values, if you take square root of this eigenvalue of A transpose A, you get singular value of A.
Okay, what does singular mean?
Singular, see, singular, this is a term use. Okay, let me go to its more detail of mathematics. So the first equation that you wait. Yeah, okay. This equation which you have seen, A equal to U sigma V transpose. So when the makers made it, the original founders, okay, what they said this sigma, the diagonal matrix, whatever is there inside it, we will call it singular. In U, whatever the columns, we will call it left singular, and whatever there are in V, we will call it right singular. So this is just a terminology used while making this particular theorem.
It has nothing to do with like we say, like for
Singular matrix.
Yeah, it is not the same as that, right?
Not as far as I know.
Okay.
Okay, so this was just the term. I mean, sir has never used these terms, but I want to tell you this, that in U, we call it left singular. In V, whatever we have, we call it right singular. And in sigma, whatever is there, we call it singular. Okay.
So right singular is this U transpose, right? Or U?
V transpose. So
yeah,
in center, singular. Whatever is to the right of singular is right singular, and whatever is the left to singular is left singular. Okay.
Sir?
Yeah.
I'm still not very much clear how you compared it with PAP inverse.
What? Okay,
Like,
inverse AP. Okay.
Yeah, how you compared with it.
Yeah, okay. I'll tell you.
Yeah, please.
I think this is a board, right?
Yes.
It is visible?
Yes.
Okay. So what we say when there is a real symmetric matrix, we call A equal to correct?
Yep.
Where A is a real symmetric matrix and P contains the eigenvectors and D has eigenvalues in the diagonal, correct?
Yes.
Now, if I say A transpose A, equal to some B.
Okay.
And then I say sigma square is equal to some C. Okay. So what equation that we obtained? It was like B equal to U, then C, U transpose.
Yes.
We got that, right? Now
Yes.
what we know, U transpose equal to I,
Yes.
correct? Or I
Yes.
can say U transpose equal to U inverse,
Yes.
correct? So I can write B equal to U, then U inverse.
Equal to C. Yes.
Correct?
Hmm.
Okay. Now
Got
let
it.
me call V equal to U inverse.
B equal to.
So can I write B equal to V inverse CV?
Yes.
Correct? And now this is
Yes.
similar to A equal to P inverse DP, right?
P inverse. Yep. Yeah. Got it. Thank you.
Got it. Okay.
Yeah.
Anyone else having doubt in this?
No, sir.
Okay. Okay. So these things are clear, right? Any doubt in this?
No, sir.
Okay. Next, important points about the singular value decomposition. Okay. The first and foremost important thing is why we are using singular value decomposition and why it is so popular. That is because singular value decomposition is guaranteed for every matrix. Okay. Next thing is A transpose and A transpose A have same eigenvalues but different in numbers. Can you tell me why?
Because
Anyone else?
are different, right? Both after transpose.
yeah, because one we are taking the row space, the other is column space, right?
Yeah, so say, if A is M cross N, A transpose is going to be some M cross M and A transpose A is going to be N cross N. So for a square matrix having M size, there will be M eigenvalues. For N size, there will be N eigenvalues.
N
So
eigenvalues.
the values will be equal. And why values are equal? They will be of different numbers. That is clear.
Because the scaling will be the same, right?
That is because of the equation that you saw here. Let me tell you. This A transpose A, you are getting V sigma square V transpose. And for A transpose, you are getting U sigma square U transpose. So what this diagonal matrix contains? Eigenvalues.
Yes.
And it is same for both cases.
Yes.
So eigenvalues are therefore same. Correct?
Yes, sir.
Next, U contains information about column space of A. And V contains information about row space of A. Okay. So these things, while I'm saying column space of A and row space of A, it seems very theoretical and mathematical. But if we move to some real life application, these things will be like very, very easy to grasp. Okay. So I'll tell you, some example of it also. So, okay, let me tell this. So suppose there is a photograph in which there are 5-6 people. Okay. Now, if I want that photograph, if I consider now every photograph is made up of some pixels. So that pixel is in a matrix form. You people know that, right? Image.
Yes.
Okay. Now each entry is like a entry of a matrix. So if you consider one particular column, second particular column, third particular column, all these can be can be related to a particular person. So suppose there are 5 persons, I'm just giving you a simplistic view. And for each person, I make a column having 4 pixels. So the matrix will be of what size? 5 people, 4 attributes. So the matrix will be 5 cross 4. Correct?
Yes, sir.
Okay. So that 5 cross 4, if you want to find it singular value decomposition, now you will contain most of the information in whatever is there in that 5 cross 4 columns. And we will contain information in 4 cross 5 rows. Correct?
Yes. Yes. Yes.
Okay. Next, sigma tells how important are columns of U and V for data retrieval. So see, sigma, what sigma exactly does? Sigma is a diagonal matrix having elements only in the principal diagonal. Now, there is one thumb rule. Thumb rule or a singular value decomposition is done because of that. When you are moving from up to down, the value of sigma goes on decreasing. So you take the highest sigma at the top. So suppose there are 5 sigmas, 5, 3, and 2. You write 5 at the top, 3 next, and 2 next. So the first element or the first column of U and first column of V transpose are most important because they are corresponding to sigma equal to 5. Similarly, the second column of U and second column of V transpose are second most important because they are corresponding to sigma 2. So and so forth. So basically this sigma has nothing but it is the matrix which sets the priority of the data. Okay.
So
Yeah.
when we take V as well, because we have the first calculation we usually do is with V, right?
Yeah.
So when we take V as well, so we take the columns accordingly.
Okay. So see,
with the highest priority.
Okay. U and V, these terms, sir has used Q1 and Q2. So don't go by term. So when I'm saying U here, U means it has come from A transpose. When I'm saying V, it has come from A transpose A. So that way you keep in mind. So whatever comes from A transpose will give me information about column space. Whatever comes from A transpose A will give me information about row space. And the first column of the matrix which comes from A transpose is most important. First column of one which comes from A transpose A is most important. That is because the singular values are arranged as such.
Yeah.
Okay.
Yes.
Next, all singular values are non-negative. Can you tell me why?
A square root, right?
A square root.
So square root of a negative number. Why there is no negative number?
No, because
Sigma square, right?
sigma as such, V it is square, right?
Correct. Those two equations you are relating to it now. So because we are saying A transpose for A transpose we are getting U sigma square U star, and for A transpose A we are getting V sigma square V transpose. So square is there. So therefore all singular values are going to be non-negative. So next question that I have is, can singular value be 0? Can it be 0?
Yes.
Yes.
Correct. It can be 0. So when I am saying non-negative, it doesn't include 0. So 0 is there. 0 can be there. 0 or positive. Okay. Next, singular values are arranged in the order of importance. Now keep this thing in mind very, very clearly. This is the most important part of singular value decomposition. Singular values are arranged in the order of importance. And why I'm saying this? This is not for some mathematical or calculation part. This is because of the real life things that you are going to do with SVD. So whenever you are going to use SVD, just keep in mind singular values are arranged in the order of importance.
What is the meaning? I'm not able to get that meaning.
Yeah. So okay. Yeah, correct. So suppose there is a set of data. So suppose I want to predict income of a person, okay, based on his education level, years of experience he has, and okay, two parameters. based on education level and years of experience. I am trying to predict his income. Okay. Now, suppose there are 100 records that I have, and I have taken those records from the person himself. Okay, so I have given them a form and I have made them fill a form. Okay, now suppose 95 of them have written correct information. They have given right information. Okay, I'm audible, right?
Yeah.
Yes.
And 5 of those have written something wrong, knowingly. They have given wrong information. Now, what will happen when you train the model? What will happen? Your model will be biased towards 95 results.
Yes.
Correct? And those 5 results will be something which will be making your model bad.
Yeah.
Now, what happens in singular value decomposition? Those 95 data points will get highest priority, and those 5 will move to the last.
Okay.
So this is the order of importance. So what is the data quality? Which particular data records are the best? Which particular records are not the best? Which particular features are the best? Which particular features should be ignored while making your model? This is what SVD does.
So it is arranging in such a way that the features with the most variance among the data set.
Arranging, in a sense, you are not arranging. The mathematics of it is automatically arranging it.
Yeah.
Correct?
So can you explain how can eigenvalues of A transpose and A transpose A are different in numbers?
Different in numbers. Okay, I'll explain that. Where is this whiteboard? Okay, now suppose A is a matrix having 5 rows and 3 columns. Correct? What will be A transpose dimension?
3 cross
5.
3 cross 5, correct?
3 cross 5.
3 cross 5. Okay. And A has a dimension of 5 cross
3.
5 cross 3. Now, if you find A transpose, what will be its dimension?
5 cross 5.
5
cross
cross
5.
3, 3 cross 5. Correct? So the dimension that you are getting is 5 cross 5.
Yes.
What will be for A transpose A?
3 cross 3.
It will be 3 cross 3 by the similar logic. Now, can you tell me one thing? If there is a square matrix which has 5 cross 5 size, how many eigenvalues will be there with it?
5.
5.
And for a 3 cross 3 matrix?
3.
So are you clear why I am saying different in numbers?
Yes, sir. Yes.
3.
Yeah, who has that doubt? Is it clear?
So is it in A transpose eigenvalues will be like repeating?
It can be. They can be repeated.
Sir, does it mean A transpose have multiple eigenvalues with the same value?
It can happen. It can happen. There can be repeated roots.
It cannot be distinct, no, when we are saying eigenvalues are same.
Or is it that like
See, what I am saying, suppose now A transpose A is 3 cross 3. Okay, so it will have three eigenvalues. Suppose 1, 2, 3. Now it will have something like this: 1, 1, 2, 3, 3. Okay, so 1, 2, 3 will be there, but they will be of different numbers. I mean, their multiplicity will be different.
Simply, we can say that A transpose will contain all the eigenvalue of A transpose A.
Yeah, you can say that. That's clear by default, because whichever has the smallest order will contain all the eigenvalues. So if I had a situation where it was 7 cross 4, then what will happen? Now A transpose will contain all.
Yeah. At max, only 4 distinct will be there.
Yeah, correct.
I had a query. So when we were learning about real symmetric matrix, we were saying for real symmetric matrix, if the eigenvalues are not same, then it is not
Eigenvectors are not
orthogonal.
independent, something like that.
It is not orthogonally diagonally.
Yeah, correct. Got you. So if there is a matrix which is having repeated roots, like this, repeated eigenvalues, then what will happen? Whatever you find eigenvector, suppose for 1, whatever is the eigenvector, let me call it some A1. So there will be 2 eigenvectors corresponding to 1, and for 2 there will be 1 eigenvector, right? Let me call it A3. Now A3 will be independent, linearly independent to A1 and A2, but A1 and A2 will not be linearly independent.
Right.
Okay.
So this doesn't affect the sigma square.
No. Therefore, we are saying singular value decomposition are universal. They are there for every possible matrix. They have no such constraint. So eigenvalue decomposition fails in many cases, but singular value decomposition is always there. It's
But we are taking A transpose and taking the eigenvalues only, right?
So that it has no effect on A. See, A transpose and A transpose A, that we are doing just to find U and V. But finally, we are dealing with A, right?
Okay.
So repeated roots have no, it doesn't affect singular value decomposition for sure. It affects eigenvalue decomposition only.
Can you please repeat how do we get sigma? I just forgot.
Sigma?
Sigma square for SVD.
Okay, I'll tell you. So now, what was A? Okay, I'll better write in text. So you are able to comprehend whatever I'm writing, right?
Yeah.
Yes.
Okay. So A was equal to U, then sigma, let me call S, and V transpose, correct? Now, if I find AA transpose, it will be equal to U sigma V transpose. Then let me find A transpose first. What is A transpose? A transpose is nothing but
U transpose.
Yes. It will be US V transpose. So V transpose U. So it will be V S transpose and U transpose. Correct?
Yes.
Yeah. So A transpose will be US V transpose, then V S and U transpose. Correct? So AA transpose will be equal to, now V transpose V is nothing but I and S U transpose. Correct? So AA transpose is equal to I, we can SIS will be equal to S square, correct?
Yeah.
And U transpose. So this is for A transpose. Similarly, you can do for A transpose A. Got it?
Yeah.
Okay.
Yes.
Okay. So any doubt in this? Any other doubt?
Yeah. So in the other example, there are one is having 5 eigenvalues and second is having 3 eigenvalues.
Okay.
Okay. So those 2 eigenvalues, so 3 eigenvalues will be equal, right? In both cases.
See, there will be same eigenvalues with different multiplicity. So their numbers may be different. If there are, for in 3, suppose there is eigenvalue 1, 2, and 3. So in other, there will be 1, 2, 3 only, but 1 can be repeated, 2 can be repeated, or 3 can be repeated, or either 2 of them can be repeated.
Okay. So all it can be 0, other 2 can be 0 as well, right?
It will be same, it won't be 0.
It may be same. Yeah, okay, got it. Yeah.
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 Okay. So can I move ahead?
Yes, sir.
Yes, sir.
Okay. Next, the application part of it, many people asked about this. So first thing, singular value decomposition is going to form the basis for PCA. That we are going to discuss in the next on-demand session. Okay. So because I did not want to mix those two things. So suppose we are studying SVD today and we again go to PCA, it will be a blunder. So let's keep them separate. But keep this thing in mind, singular value decomposition is going to form the basis of PCA, principal component analysis. Again, principal component analysis is one of the most used tool in machine learning and data science. It is used everywhere. Almost in every model that you build, PCA is there. Okay, so SVD forms the basis of it. So this is the first importance of SVD. Next, SVD can be used to solve AX equal to B even if A is not rectangular. Sorry, A is not square. That is, A is rectangular. Can you tell me what this point is, second point, if you are understanding anything from it?
It means, sir, it will give us lambda values.
Okay, so in general, what happens? If there is a system of equation where A is square matrix, we easily solve it, right? X equal to A inverse B. Because A inverse is possible only in case of square matrix. So if A inverse exists, X equal to A inverse B, we directly do and find. And there is no problem as such. But if there is a case where A is rectangular, there are few methods like LU decomposition, if you have heard of. Then there is other methods also. There are 2-3 methods. But SVD is also a very important method, and it is used when the data set is very large, in millions. There also we can use SVD because one of the most important and beautiful thing about SVD is it is scalable. It is highly scalable. So even if your data size is very large, very small, medium, whatever is the size, SVD can be used there. Next is used for dimensionality reduction. So if any one of you can enlighten me with dimensionality reduction. What is dimensionality reduction?
Basically, if we have a feature matrix which is in D dimension, we are reducing it to lower dimension.
So, and what are the two functions used there?
You mean encoder and decoder?
Encoder and decoder.
Yeah, correct. Encoder and decoder. So basically we use encoder and decoder for dimensionality reduction. Okay. So is there any method where we can increase the dimension as well?
The original data set.
Yes. Yes, mathematically we can do that. Just the reverse of dimensionality reduction.
Okay.
Just reverse encoder decoder.
Okay.
Dimensionality expansion instead of reduction. Next application is image compression. Now image compression again, let me give you an example. So suppose there is an image of a cat and okay, so I think you may have used this in many times. What happens if you are uploading a picture for a particular website, so it demands that your picture should be of 50 KB, not more than that. And suppose you have a image of 2 MB. What you do, you go and compress it by using your offline apps or your any online website, right?
Yes.
So there SVD is getting used. And how it is going to do that? So suppose there is a person name whatever X in 2 MB, that person X looks same as that 50 KB person X, correct? So that is happening because the order of importance is maintained. The order of importance of the pixels are maintained. So whichever is the most important record or the pixels, they are kept. That is also done using SVD. So basically you are removing the all non-important pixels and keeping the important pixels. But since the number of pixels have reduced, your image is getting compressed. Okay. Okay. Next is search engine optimization. So if you know, so whenever you search for any particular thing, suppose you search machine learning in Google tab. So what will happen? There will be 1, 2, 3, 4, 5, many search results, many pages get opened. So that is also done using this single value decomposition. So there they are using this again, feature importance property of singular value decomposition. They are using it in Google optimization or Edge optimization, wherever, or Internet Explorer, wherever you are doing it, search engine optimization is done using singular value decomposition. Next then is facial recognition. So facial recognition, I can give you an example. So suppose there is a person and he has not used his FB for long and he forgets his FB password. So there was a way, I don't know now it is there or not, but few years ago or few months ago at least, there was a feature that while you log in, they give you many pictures, identify this particular person, right? Any of you have gone through that experience?
Yes.
Yeah, identify this person is your friend, so what is his name, whatever. So if you identify some 10 out of 12 or 13 out of 15, then you are like, you are the authentic person. So there also this algorithm is getting used, facial recognition. Okay, SVD is getting used there. Next is recommendation system. So in case of Amazon, Flipkart, there are various other methods also, but SVD is also one of the methods which is getting used for this recommendation system and all those things. Okay, correct?
Yes.
So apart from solving any numerical, that I think we will do now. Any other thing that you want to ask me in this particular process? At least SVD is clear by now or not?
Yes.
Its importance.
One question: is there any pointer where we can just go little deep dive on how it is used for solving AX is equal to B or for a rectangular matrix? And whatever use you have given, if we could just look into the details of it.
You feel free to go to any of the application. That is not the scope of this course, at least.
Yeah, I know. No, I'm saying any pointer you have so that we can just do the deep dive ourselves.
I think you won't find any particular material. I mean, you won't find anything stacked somewhere. So if you go for search engine optimization, you can find many sources, books and all. But I don't know where SVD they will relate to it or not. So you go, I mean, whenever you do a project or something, no, you will understand it more. So you can see, I mean, image compression. For image compression, SVD codes are there on GitHub. A lot of codes are there. A lot of people have posted. So you can go and search that.
Okay.
So for image compression, I'm sure. Search engine optimization, see, SVD is a very small part of it. There are other methods also which are there. For instance, there is something called LSTM, which is also used with it. There is something called TF-IDF that is also used. Then cosine similarity, all those things are also used for search engine optimization. So it is a small part of the whole lot of things. So if you go into search engine optimization, it is a course in itself. Maybe 2-3 terms you will take in search engine optimization if you want to grasp it fully. But again, having such questions is highly welcomed. If you are asking such questions, it means you have interest and you want to study it. So go for it, whatever time it takes.
Okay, sure. Thanks.
Yeah. So I appreciate all of you. If you find some, I mean, go and have these applications and search it on Google, you'll find something or something else.
Excuse me, sir.
Yeah.
Sir, can we say that I know we are not doing PCA today, but within PCA, the logic of finding X tilde is similar to what we do with SVD, is it?
Yeah, see, if I go into mathematical details of SVD, it is nothing but, okay, I'll tell you, I don't want to prove it mathematically, first thing I'm saying. SVD, basically what it does, it finds the direction in which a matrix stretches a unit vector most. Now, it seems complicated.
Yes.
Okay, you understand it?
Yes, yes.
Well and good. Okay. So what happens if I go mathematics wise? So suppose there is a matrix A and there is a vector X. So finding SVD is nothing but finding the argmax of X length. Okay.
Okay.
So if you are going to find the argmax of Ax, it is similar to finding the argmax of Ax square. So if you are finding so you have solved many optimization problems. You may have solved this f dash x equal to 0 problems. What they are called?
Yes.
Minimum maxima problems.
Minimalization.
Yeah, minimum maxima problems.
Yeah.
So if you want to find maxima of suppose root over of x square minus x. So what is the standard practice? You square the function first and then find x by taking df square x by dx square.
Okay. Okay. Yeah.
Correct. So argmax of Ax will be similar to argmax of Ax square.
Yeah. Yeah.
Now, how to find this Ax square? That is nothing but suppose I want to find x square. So where x is a vector, x square, I mean x square length of x square. What I do x transpose dot x or x dot x. If you find x dot x, dot product is nothing but square of the length.
Yes.
Correct. So if you are finding Ax square, it is same as argmax of x transpose A transpose Ax. But we are saying that A transpose A, again, A transpose A is nothing but a real symmetric matrix. So you can write it in eigen decomposition form. So if you write and do all those things, so basically finding argmax of Ax is nothing but finding the maximum eigenvalue.
Yes.
So in PCA also you will find the similar thing.
Yeah, I had that doubt. That's why, like, is it the same? Like the principle behind that seems to be the same thing, because over there too we are minimizing the extent of error we get when we reconstruct, right? So basically,
maximizing variance is similar to finding the maximum lambda.
Yes. Yes, correct? Because so that is a maximum stretch that we get.
So in singular value decomposition, what exactly you are doing? You are arranging lambdas in order of priority. So that is nothing but highest to lowest.
Yes.
So so the basis behind PCA is SVD.
Yeah. Okay.
Okay.
Yes.
Okay. Any other doubt? Anything?
Sorry, a very basic doubt is not from this SVD part. What is the permutation matrix?
Okay, permutation matrix, you are still with that. So permutation matrix is a matrix which has 1 0 as the element. I mean, there is only one in a row and rest all zeros.
Okay.
So identity matrix is also a permutation matrix. Okay. Any other doubt? So from week 3 and week 4 also, if there are small doubts, I can clarify that. Okay, so I think in proof also, in singular value decomposition proof, there are so many parts where I think you may find it tough, but try to solve it. I mean, I didn't knowingly write all those steps related to, because those steps and all you can any day go and watch the lectures and find. I wanted your intuition to be clear behind singular value decomposition. So I think it is clear, right? Any doubt in this? Even if I am 70-80% successful, I'll be happy.
No, sir, it is clear. So far, it is clear.
Yeah. So the intuition behind SVD is, yeah. Yeah, go ahead. Anyone, someone was speaking. Okay, so we may solve a question. I think yeah, any doubt in any doubt? I mean, just be easy enough and ask. It's okay to ask questions. Go ahead.
Are we doing week six today?
No, week 6, I think if we do it today, it will be too much. So because week 6 is going to take positive, definite, and all those things, and then PCA, that is going to be.
Okay.
So I knowingly I requested the people concerned to have 2 sessions, not 1. That we go slowly about these topics. These topics are very important.
So when is the solve with instructor week 7?
I have no idea about it.
Okay, it was yesterday, but
Yeah,
it
so
got cancelled.
there was a technical issue. I mean, the
Yeah.
person who was going to take it, there was some issue in his locality throughout. So therefore it got cancelled. So it will be scheduled very soon. That I got to know.
Actually, today it is due date for the assignment, so it would be helpful.
Okay, so what is your doubt in week 7? You may ask.
Sir, I'll
Yeah.
update. It is changed to 22nd Wednesday, the due date.
Acha, it is shifted to 22nd.
Yeah.
Okay, okay. Thank you.
Good. So if you have any doubt, I mean, I can try to explain your doubt in week 7.
No, sir, but before solve grading assignment, we tried to solve with instructor, so it would be really easy.
Okay, then it's fine.
That's the point only.
Okay. So week 3, week 4, any doubt? I mean, there were some people who were asked questions about it in spreadsheet. So anyone?
All clear, sir.
All clear. Week 5, I think, is this way correct? I mean, I can go ahead with this way in week 6 also, or you want me to do something else? I'm ready for feedback.
We solve one problem.
So we wanted one problem to be solved.
Okay, so let's solve one for week 5 right now, SVD. Okay, and week 6, I'll include problem in slides itself. Okay.
Yes, sir.
Okay. So SVD, let's take a small problem. Okay. Let's take a imagine. That will be fine. Okay. Now suppose I'm audible, right?
Yes, yes.
Yes, sir, you are audible.
I'm not able to move this whiteboard. Do I need to erase it first? Yeah, okay. Okay, suppose there is a matrix A. It will be good if you solve with me. 1, 2, and pardon my handwriting. I'm trying to write it using mouse. I don't have any writing material right now. So if there is a matrix like this, okay, and you want to find its SVD, so what will you do? Step 1. What will be step 1?
Take A transpose.
Yeah, find A transpose A. First step.
Yeah, A transpose A.
So can you do it with me?
Yes, sir.
Yeah, and give me the result.
What?
Okay, tell me first thing. This A, is it a square matrix? Is it a symmetric matrix?
No, it is not symmetric.
Okay, so if it's not symmetric, we cannot say its eigenvalue decomposition will exist or not for sure. Now we know it will exist because eigenvalues are distinct, but there can be some cases like this: 1, 0, 2, and 1, where the eigenvalue decomposition will not exist.
Yes.
How do you say eigenvalue do not exist?
Why? What?
How do you say that does not exist?
This is because eigenvalues are repeated.
Not distinct. Okay.
But here eigenvalues are different. So its eigenvalue decomposition is possible. But SVD is in any case possible. SVD is possible for everything.
So you need A transpose A.
Yeah, A transpose A, what is the value?
It's 1228.
1, 2,
28.
2, and 8. Okay. Now next step will be what? Find lambdas of A transpose A.
So we can make the characteristic equation.
Yeah, first find the characteristic equation, which will be 1 minus lambda, then 8 minus lambda minus 4 equal to 0. From this, find lambda.
Lambda. So
Yeah, anyone calculated?
It is irrational.
Irrational.
Like we get a square root.
Yeah, square root of what?
We get and like I got 9 plus or minus square root 65 by 2. The whole by
9 plus minus.
this. No, the 9 is outside the square root. 9 plus or minus root 65 the whole by 2.
Correct?
That is what I got.
Yeah, I too got the same by 2.
Okay, fine. That's fine.
By 2, by 2.
By 2, yeah.
Yeah, the whole by 2. Yeah.
Okay. So that's fine. That's okay. Root 65. Now, can you tell me what it will be? Its value, it will be around 8. 8 point something, right?
Yeah, 8.062.
Why 8.06 something. So lambda will be, can you tell me in decimals what will be its value? So it will be 917 by 2. Let's take its 8.5. And then there will be 0.8 minus 8, 9 minus 8.1 is 0.9. Then there will be 0.45. 8.5 and 0.45, correct?
Yeah.
Yes, sir.
Yeah. These two will be lambda values. Now find sigma from it. Sigmas or the singular values will be nothing but square root of 8.5 and square root of 0.45. Now see, here only it is clear that whatever is corresponding to 8.5 is significant and 0.45 will be neglected. So I'll come to it. Okay. So let's go to the next step. Next step is for sigma, right?
Yes.
So sigma is nothing but just write these singular values in decreasing order. So here root of 8.5, it will be around 2.9, I guess. 2.9 or 2.8.
Yes. 2.92.
2.92. Okay.
Yeah.
So let's call it 2.92, then 0, 0, and 0.45. So 0.66. 0.6. What?
0.67.
0.67. Okay. So 0.67. This is my sigma. So I have got sigma. Next. How to find U? Sorry, not U. Since you are saying A transpose A, so A transpose A relates to what? V.
Yes.
Correct? So
yes.
Since you have found eigenvalues, find corresponding eigenvectors. So eigenvectors, can you find out?
Yes, sir.
Go ahead and find. So whatever eigenvector you find, you normalize it also, right?
Yes.
Normalize it too. V2. Yeah, anyone got the value?
Sir, I got the first eigen vector that is corresponding to
8.5.
Yeah.
What is the value?
0.258 and 0.966.
0.26 and 0.96. Okay.
Yes, yes.
Okay. So this is the eigenvalue, first eigenvalue. This is normalized.
Yes, yes, it is normalized.
Okay. Now V2 you will get something again. Let's assume some value. Let's take 0.15 and 0.65, whatever. Okay. So this will be your next step. So what you did, first step you found A transpose A. Next you find lambdas of A. Then you find sigma. Then you find this big sigma. These are the steps. Next you find eigenvectors corresponding to lambdas that you have obtained. Normalize it. This is the next step. Next you find U. So up to this you have found V. So V will be nothing but stack V1 and V2 together.
Yes.
This will be your V. Okay.
Yes.
Now next step is finding U. So how will you find U?
Is 1 by sigma times A times the corresponding eigenvector.
Correct. So that is one of the methods. So that is the method which Sir has used, 1 by sigma A and V1.
Yeah, corresponding.
This will be U1 and U2 will be equal to 1 upon sigma 2 and AV2. Correct?
Yes.
Okay. There is another method which is which I use generally. That is use this AV equal to sigma U.
Yes.
So from this you can directly find U. Okay.
Yes, sir.
This is again a method AV equal to sigma U, because V you have already found, A you already have, sigma you have, so AV equal to sigma U gives you U directly.
Yes.
So this method, I mean both methods are correct, but this requires calculation at micro level. This is a macro level calculation.
This is almost from the initial equations that we did with sigma square.
Yes,
right?
yes, correct. This is from the basic equation, where we are writing like this. Where we are writing A equal to U sigma and V transpose. So actually V transpose is nothing but V inverse, right? So if it comes this side, it will become AV equal to U sigma.
Yes, yes.
So from this I generally do. Okay. So any doubt in this method? Method is clear, right?
Yes, sir.
So
Yes.
if you want, we can make a note of the steps that we did for everyone. So what was step 1? Find A transpose A, correct?
Yes.
Next, find its
Eigenvalues.
Eigenvalues and eigenvectors. Okay. Third is normalize eigenvectors. Fourth is find singular values. Okay. Fifth is find diagonal matrix by stacking singular values increasing order. Okay. Next step is find will be by stacking normalized eigen vectors. Next, 7 is find u using
AB equals 6.
calculation or b equal to u 6. Okay, this is what we did. This I'll add to the slide also maybe.
So,
Any doubt in any of the slides or any discussion that we had? Free to ask anything.
no, sir.
I thought in on-demand session there will be a lot of questions, but
I think like this one was a bit more useful, like on a conceptual level, right? So, like it helped to like, strengthen the understanding of the concepts behind the topic.
yeah, oh yeah. So see, the thing is, when a professor is teaching all these topics, he is more concerned about the mathematical aspect of it. He wants you to understand everything mathematically because he is thinking in terms of deep research and all. Okay, so sometimes you may not relate to it, but while we are talking, we talk more of application things and all. So that is more relatable. So go and see all those lectures again, see the derivations and all. I think those will feel more relatable now. So you may be now in a better place to understand SVD.
Yes.
Yes.
PC and all we will cover in next session whenever we have, I think next Sunday or Saturday. Okay. So
Okay.
if there is
next Saturday, next Saturday and Sunday, we have some OPP and ROE. Please schedule the session without clashing with those OPPs and ROEs.
yeah. So that calendar thing will be managed by people who are there in machine learning foundation. I mean, they will manage it. Don't worry about it. So there will be no clash. Don't worry about it. Okay. So if is there any doubt? Again, I am asking.
No, sir.
No, sir.
Yeah. So was the session helpful to all of you?
Yes.
Yes.
Yes, sir.
Okay. So this length of matrix, something I'll go and search. Why I said like that. Rest all I think is very clear. So okay. Then I think we will meet in next session. If there is no further doubt.
Yes.
Yeah.
Yes.
Yeah. Okay.
Thank you.
Thank you,
Good
sir.
day, all of you.
Thanks,
Sir,
sir.
one last thing. We'll be getting these slides.
Yeah, I'll share it with you. And see if there is any other doubt, any other session you want, you may ask. I mean, we can have discussions. There is no such issue. I mean, people in MLF, in machine learning team are very open to discussions. So just feel free to discuss whatever you have. Okay.
Yes, sir.
Okay then.
Thank you.
Good day, all of you.
Thank you.
Thank you so much.
Thank you.